So thank you very much for giving me the opportunity to talk at SEM Israel Tech Webinar this year. So I'm talking about the change of contact resistance of a broken socket in HTOL conditions, which is a very, very hot topic. So first of all, who am I? So my name is Bernhard. I'm product manager at Yamaichi Electronics in Munich. We have also a sales representative in Israel. It's Amit Lampert. He's local there. So if you have questions, of course, afterwards, you can, of course, contact me directly or also contact Amit. So some words to Yamaichi. So Yamaichi comes traditionally from burn-in and test sockets. Here in Munich, we develop also other products like test adapters and also test fixtures, but also have at Yamaichi a lot of connectors, either for automotive industry or industrial. We are located global, so headquarters, of course, in Japan. We have there are many production sites. There is also sales offices in Asia. Then in US, we have also sales and production site. And in Europe, we have here the location here in Munich, but also sales and engineering locations, but also own production here in Frankfurt Oder. Good, let's come to the topic. Change of contact resistance of a broken socket in HTOL conditions. So usually if you get a data sheet of a socket or if you need to test a semiconductor device, you want to know actually the behavior of a socket. Unfortunately, this kind of data sheets of a socket or broken just give you, let's say, data which are in ideal conditions. But what happens actually if you talk about high temperatures, long-term duration, and so on? How does the socket behave? And this is what we analyzed in the DOE. So we had we did a design of experiment here in-house in Munich. We have here a test lab and had the opportunity to set up this kind of HTOL test. What does it mean, HTOL? So HTOL is a high temperature operating live test. So the device actually, which is tested, should operate in a very in a mode which is basically very near to the reality. Of course, some parameters can be adjusted, but actually this is a non-destructive test, which should give you a predictable idea what happens with the device over the lifetime. And yeah, so we had the opportunity to build it also in our lab. So you can see actually here on the right-hand side the chamber with a rack inside. We have PCBs there, and also you can see the sockets and a lot of cables actually. And so what we did is, of course, we built this HTOL test also in terms of cycling. So we started at 20 degrees. We are ramping up this temperature up to 1.5 with a ramp up of 1.5 degrees. Hold this temperature and then coming back with -3 Celsius degrees to a room temperature. And then we repeat this until 500 hours. And then the next period is until 1,000 hours. The temperature in the chamber is set to 80 degrees. This is mainly calculated, so something I will explain later. Of course, we have dry heat. The dry heat is also specified in the DIN spec, and so that we have really no other environmental conditions than H2L. The test setup itself, so we have seen it already, some PCBs in the rack. Each PCB has sockets on it. And we have in total 8 sockets which are loaded with a DUT, with a daisy chain DUT, and they are electrically connected. The one socket here, this is a passive socket which has no electrical connection at all. This is basically to see what happens with the balls, with the socket, if there is no current and no voltage applied. The target temperature on the pin is 125 degrees. So we had also the opportunity in the socket to put a temperature sensor inside. So it was a thermocouple. And also on top of the device, there is also a temperature sensor to sensing the device of the daisy chain itself. the test current was around about 150 milliamps. So that was calculated then with a resistor and the resistance of the daisy chain as measurement resistor. The daisy chain itself, so this is it was a wafer level CSP with 269 volts. It was pitch 0.4 millimeter, and we had 10 connections. So basically, there were one big loop, which was here the input and goes through the daisy chain, also backwards to the PCB and all through the pins. And but we had also the opportunity to make smaller loops and control them. We are using a test contactor, which has a floating base design. So the floating base itself is here. This is spring loaded, so it helps also to protect the pins when the device is inserted, but also helps to align the device in the socket. It has a stiffener because of the high pin count, but it's very usual socket. The pin itself is a pin which is double side ended. Means it's there's a spring inside. All two plungers are spring loaded, and so the length in relaxed position is 5.7 millimeters. If it's in working position, we have 5.05 millimeter. The force is 20 grams. The current carrying capacity is 1 amps and with a self-heating of 30 degrees, but it's in this case not for the test itself is not so important. But what's important is actually the operating temperature. So it's specified from minus 40 degrees up to 125 degrees. And this is actually, when you have seen the before, so would like to have a target temperature on the pin with 125 degrees. This means also we are actually on the limit of the pin. And so this is, of course, a very important factor. So what happens actually on its limit? Good, what do we do actually with during the test? We monitor the contact resistance, and basically what do we have to do before is we have to do an initial measurement and set this as a baseline. So we measured all the contact resistance in the loop and manually set the right resistor there, have then calculated the applied current, and this is how we start. And then we have trigger events. So for the measurement, so we could not measure completely over the 1,000 hours. It would be tons of data actually to analyze. So we said if there is a change in the contact resistance of more than 2.5%, then we start a trigger. Or if no trigger occurs, we measure every minute since the last measurement. And this gives us, let's say, also a lot of information, but it can be more analyzed afterwards. So what do we do actually when a trigger event occurs? We measure the temperature on the DUTs and the socket and measure the contact resistance. And this contact resistance is then set as a new baseline. During the readouts, so of the HTOL, so at time 0, 168 hours, 500 hours, and 1,000 hours, we do visual inspections of the DUT bolts and also of the pins to see if there's anything happening. Let's come to the curves. So actually, the curves looks quite nice. So this is period 1. Means from time 0 to 168 hours. You can see here actually the resistance versus the time. So when this is here the ramp-up phase. You see actually in the ramp-up phase there's a kind of a peak, contact resistance peak, which was very interesting, and come back actually to a lower level on the contact resistance. There's a slightly increase overall over the whole time, which is also related not only to the socket in the DUT, but also to the setup itself. We could also see in the back, when we do the ramp down, that there is a kind of a peak of contact resistance. What we also could see is actually that the socket number 8 is somehow starting already in a very, very high level of contact resistance. So there's something which is probably not in line with the other sockets. Period 2, looks different. So there are all the lines you can see here, the blue ones, the red ones, and the green ones are trigger events which are locked. So period 2 is from 168 hours to 500 hours. So also here we have the contact resistance over time. We see that also, so it started already a little bit higher than we ended before. But also we could see that socket number 8 is going very unstable already. And but also the other socket, they are still okay in a low level, but also start somehow a little bit unstable, but still not causing some events. Period 3 looks much worse actually with in terms of triggers. So many triggering, starting from 500 hours to 1,000 hours. So also socket number 8 here is somehow going really crazy, and it's really fading. Also at the end here of 1,000 hours, it's really getting a very high contact resistance. But we also that socket number 6 failed. It's hard to see here in the lines, but actually that's the orange line here. So it's also somehow higher than the other ones, and got very unstable. Good. The results of this DOE. So as mentioned, so period 1, no events at all. So very nice graphs. Actually, no events. But we have seen on the ramp up and the ramp down that there was a kind of an increase in contact resistance and overall slight increase. That number 8 started already with a high resistance, and the increase of the resistance also was higher than the other ones. In period 2, more than 600 events occurred. So that 1 to 7 was also a continuous increase of contact resistance, but on a very low level. That number 8 got very unstable, and the resistance increase was high. Period 3, more than 2,000 events occurred actually. And as I mentioned, so that 1 to 5 and 7, there was still a slow increase in contact resistance, but on that number 6 and number 8, a higher resistance and instability occurred. And we found also out that the events are mainly caused by that 6 and that number 8. Good. Visual inspection. So of course we want to see, okay, what's happening actually on the balls and also on the socket itself. So we had this daisy chain. We divided this ball map into 30 segments, and we had 8 devices. Made the pictures at time 0, 168 hours, and also 500 hours and 1,000 hours. So we got more than 960, actually 1,000 pictures with the socket itself, and all pictures have been analyzed and viewed actually. So it was tremendous work to let's say to analyze what's happening on the balls and also on the pins. So I picked out some of the pictures, not all 1,000, but some of them, and started with that number 1 and also area number 2. So we have selected this one for all the dots to see representative if this is actually what's happening there. So in an initial one, you see actually no imprints at all. So of course it's a new daisy chain, no contacts, no contact marks. After 168 hours, you see clearly the imprints of the pin. So it's the 4 peaks of the crown pin, very good centered. So nothing which is on shearing off the balls, for instance. After 500 hours, the imprints go getting deeper. And here you can see actually after 1,000 hours, very deep imprints. What we could also see here is actually that the pin hits the balls always on the same position. So the pin itself does not turn somehow. It's hitting the peak of the pins, hitting exactly the same position on the balls again. Here you can see actually the pins itself. So the pins are slightly contaminated on the peaks, but it's not that it's very dirty. So of course there is some kind of contamination, slightly contamination. That number 8, this was the problem, the issue that I would say. Also initial, there is no no imprint. After 168 hours, there are imprints like before. After 500 hours, deeper imprints, and after 1,000 hours, also imprints. It seems that the depth of the ball marks are not that deep as before. What we could also see actually on the pin itself, there is slightly more contamination on the pin itself. So this could happen that the ball graining, so the balls itself composition is maybe slightly different than other dots we had before. Yeah, and then dot number 6, this was also the one which got crazy in period 3. Also here you can see the initial picture of the balls, so nothing special. Also after 168 hours, clear imprints, centered, so nothing went wrong. After 500 hours and after 1,000 hours, the imprints are also very clear and can be seen very well. What we have seen is that on one of the balls there's a kind of contamination. This could come from the readout. So of course we had, when we put out the device after 168 hours, 500 hours and 1,000 hours, of course we had to go under the microscope. It could happen that there kind of a contamination took place. The pin itself looks also quite nice. So of course there's contamination, but this is in a very normal way. Yeah, as I mentioned, we saw actually a kind of an high resistance when we have a ramp up, and also during our ramp ups we had also this kind of increase of contact resistance. So this was of course very interesting for us to see what is actually happening there, and is this just let's say a phenomenon which occurs randomly, or is this something we can confirm? And therefore we made a similar DOE with ELFR conditions. So it's also defined in the JDEC, so early life failure rate calculation. We had this very same hardware configuration. We had 24 runs with 48 hours, and we did this several times but with pitch 0.35 millimeter and 0.3. You can see here actually the graph. So the red dotted line, this is the temperature curve. So here we have the ramp up again with 1.5 Celsius degrees, and the ramp down with -3 degrees. Here you can see actually 15 runs. So for each run, we used a new, fresh device, daisy chain. And we did further runs, but you could not see actually because some of the lines were actually overlapped. Also, you can see here on the, I think this is run number 10, this is also somehow interrupted because of an test error. But what we could confirm is that really when we have the ramp up, the contact resistance is higher and then coming down to a certain value. And also this is the same phenomenon when we have the ramp down. So there is also a high resistance and then it's coming down to a normal level. And so this is of course something which is interesting for our customers to understand what's happening. So when there's a setup of HTOL or DOE, an HTOL on ELFR, that there is a kind of phenomenon which increases first the contact resistance by coming down. So it means also setting up this tests for reliability tests. This could be a good hint to get better results out of these reliability tests. Findings and conclusions. The contact resistance is rising from 0 to 1,000 hours constantly, but it's on a very low level. So it's really something which is it can be really must be not calculated actually. The low contamination on the pin is seen, which is normal. It can happen. Of course, here we have a very low current. The means also when we have other ball materials, if there's some other conditions of the device, and actually every customer has different conditions during HTOL and ELFR on the device, especially if we talk about higher current and more self-heating, then the contamination on the pin could be much higher. We have seen the contact resistance peak during ramp up. So in period 1, this is also like we have seen on the ELFR test. We think, of course, that the due to the fact that there's oxide on the balls, the pin hits the ball, and then after, so it has a high contact resistance. And if the temperature getting higher, then the balls getting softer, and the connection between the pin and the ball getting better. And this is then causing this ramp down on the temperature. The ramp down in contact resistance. In period 2 and 3, we saw also that we have an oxide on the ball, but in addition, actually a little bit of an oxide on the pin because of this light contamination. And then the contact resistance starts actually on a little bit higher level. And we have the same thing that when we have then the temperature rise, the balls getting softer, and the connection between the ball and the pin getting better. And so the contact resistance in a stable way. And then we have the contact resistance peak during the ramp down. So this is a little bit difficult to explain, but we think that during the cool down phase, also here it's vice versa, the ramp up phase, the ball's getting harder, and there is a change basically on the metallic connection. And this is somehow causing this jump of contact resistance during the ramp down phase. Yeah, so this is basically all what we have found out, and unfortunately, this is not something which can be written in a spec sheet, or it can be written in the kind of a data sheet. So because of, as I mentioned, the conditions are always different at the customer side, so also from device to device. Then there are probably also other pins, other pin geometries. So there are lots of factors which could influence this data. However, of course, it gives some kind of an idea what's really happening in the ramp-up phase of an HTOL or a long-term reliability test, also during the phase, and then also during the ramp down. Thank you very much for listening, and of course, do not hesitate to ask any questions. Thank you.